Welcome to today's webinar presentation, Scaling for Extreme Growth, the Data Layer is Ground Zero, brought to you by Aerospike and Intel. I would like to pass it off to Aerospike's Cheryl Sage, who will be moderating this presentation.
Good morning, good evening, and welcome. I'm Cheryl Sage, Director of Partner Marketing here at Aerospike, and it's my pleasure to moderate today's webinar on Scaling for Extreme Growth. In today's session, we'll discuss what's driving a next-gen data strategy, how scale problems manifest, and some techniques to manage them, how PayPal is approaching the data layer and system scale, and how Aerospike Hybrid Memory architecture with Intel persistent memory can help organizations scale up before scaling out. Each of today's speakers are industry experts in the art and science of scale. Our first presenter is Srini Srinivasan. Srini is Chief Product Officer and founder of Aerospike. He has 20 years of experience designing, developing, and operating high-scale infrastructure. He also has over a dozen patents in database and distributed systems technologies. Srini co-founded Aerospike to solve the real-time scaling problems he experienced while he was Senior Director of Engineering at Yahoo. Sai Devabakatuna is Senior Director of Engineering at PayPal, where his responsibilities include being an interim head of all data at PayPal, reporting to the CTO late last year. Sai is also responsible for one of the world's largest analytics and OLTP platforms, with over 350 petabytes of data. Sai has over 20 years of experience in all things data, with 15 of them being at PayPal. Athreya Gopalakrishna is Senior Database Engineering Manager at PayPal, where his responsibilities include NoSQL distributed databases, database automation software, and software lifecycle orchestration engines. Athreya has over 17 years of experience evaluating, architecting, and operationalizing databases for large-scale performance. Now I'd like to hand it over to Srini to take us through what's driving a next-gen data strategy. Over to you, Srini.
Thank you, Cheryl. So let's look at what's driving the next-gen data strategy. What we're seeing today is that user behavior has changed over the last 15 years to the point where every consumer would like to would like access from anywhere, from any device, potentially watches, mobile phones, iPads, computers, cars, etc. The desire for personalization is really important because everyone expects to get the best possible experience for themselves without wasting any time at all. And more financial transactions, for example, as well as all kinds of online shopping are now becoming ubiquitous, especially this year, with governments around the world urging citizens to stay at home. To give you an idea of the scale of this, most recently, PayPal has reported a 22% increase in their payments to about 200 billion last quarter. The interesting thing here is at the consumer level, essentially everybody, virtually everyone, 81% want personalization. However, only 31% of companies are using machine learning to deliver it. In fact, IDC's white paper predicts that nearly 30% of the global data sphere will be real-time by 2025. And what exactly does real-time mean? In order to make the usability, I would say, really interesting to use, to human beings, essentially you got to respond within the time of a user's ability to concentrate, so to speak. How long are they willing to wait? Typically, it's about 100 to 200 millisecond end-to-end response time. Now, with apps and machines, it might be even shorter than that. Now, the round trip has to be 100 to 200 milliseconds for the user. What that means is everything in the middle of it, which is in the process of delivering that user experience, has to happen much faster. And as you kind of go down all the way into the database, which essentially is needed for personalization, the kinds of response times that are required of the database in terms of reads and writes is sub-millisecond. And in order to produce a really good online user experience, we end up with a sub-millisecond requirement on the database. And we will see some of that as we go forward. Please. So I'm just going to take you through a few use cases which are common, and then hand it off to Sai. Essentially, if you look at something like healthcare, there are applications today that are essentially monitoring people for certain vital readings, if you will. It could be in terms of heartbeat, it could be in terms of sugar levels and so on, and are able to provide a real-time escalation, if you will, in case a certain problem is detected. And to actually deploy this, we have the technology today to be able to deploy it at scale. And this will also require not just an Internet of Things kind of model where a vast number of these devices are used for monitoring, but it's also done in real time with reaction times which are at the level where we can avoid any crises at all, rather than solving crises after they happen, especially health crises. And in terms of other kinds of use cases, if we go towards Customer 360, what we have is machine learning and AI-based algorithms generating models, and then using the user's personalized data to make decisions in real time, and to reduce the cycle of generating the model to producing the actual decision. We're now able to reduce these cycles to hours from days, for example, and sometimes, depending on the amount of data, we could even make the cycle time reduced to minutes. And then if you move to financial services, for example, the ability to detect fraud in transactions as the transaction is being executed is really important. This solves a lot of important problems because it is much harder to claw back funds after a transaction is committed if the fraud is detected too late. In fact, PayPal is an expert in these kinds of machine learning and AI models for fraud detection. I'd like to now hand over to Sai so he can basically talk about the art and science of scale.
Thank you, Srini. Good morning, everybody. Hope all of you can hear me well. I hope all of you are doing well. So I'm currently responsible for all things OLTP database platform at PayPal. The scale is one of the leading concerns every year before we head out to holiday peak season in November. And it has become an integral part of our lifestyle. And the analogy here, stated here in this slide, it's not the load that breaks you down, it's the way you carry it. That sums it up. The scale needs to be a well thought out strategy, and it should not be an afterthought exercise. And it has consequences all the way from the design to the infrastructure layer. It is not the job of only the infrastructure people. The scale strategy needs to be well thought out across the company. So to talk about how the scale problems manifest, they show up as a performance problem. They can show up as an availability problem, or they can show up as a partial degraded service problem. But it's easy to misconstruct the scale challenge as an availability challenge and solve it that way, and the performance problem by throwing hardware at it. And all of these will only complicate the system further and not solving the scale problem. And it's important to understand the trigger, and scale problem, and hence is integral part of whether it is a performance or it is an availability, the goals that we may have. And why is scaling a big deal? And we have heard many, the strategies about, the scaling should be a database problem. It should be an underlying infrastructure problem. An application can just focus more on shipping the features. While that is generally true, but it's important that everybody has a role in that, because scaling is not just a problem at the infrastructure level. It is, we look at it holistically as a system and how they interact with each other. The scaling a particular service, be it a database service, be it an infrastructure service, they can be, the approaches there is, it's more like a science. Then you can go by the data that is showing and then scale accordingly. When it comes to scaling a system, you really have to understand the overall architecture of how they interact with each other, how your customers are going to interact with your system. Only with that insights, you can have a scale strategy that evolves as your system is evolving. And that's why scaling a system is more of a science, more of an art than science. The dimensions of scale, it's very easy to start with scaling just means horizontal scale and we're done with it. In fact, that may create challenges when the concurrency starts showing up as a scale challenge. More often than not, scale out is a popular way to scale any single service out there. But when you're looking at scaling a system, it's not just about scale out or scale up. The concurrency becomes a dominant factor when you're looking at the holistically as a system. And the scale out is a well-known thing. I'll not spend much time there. Scale up is equally important. In fact, I would suggest that we need to start with first the scale up before we scale out. And there needs to be that balance of the size of a given node before we start scaling it out. The concurrency is a very important part of the dimensions of scale. The things like connection management, the shared resources on any given node, intra-cluster traffic, the cluster state management, all of those becomes a part of the concurrency. And any distributed system will have some concurrency related scale challenges to work through. It's important to identify what those are and ensure that your system is well architected to scale in that dimension as well. And here, some of the strategies to adopt here is why the scale strategy is an important thing to think through all the way from the design stage to development, all the way then to the production. And it needs to be that continuous loop of the life cycle. The customer experience is the most important factor when it comes to the scale strategy. For example, is it okay to serve fresh data for all experiences? Or is it okay to provide some stale data, like a social networks, right? It's okay to provide few seconds stale data, as long as you as the user, if you're the one making changes, you can see those changes right away. Everybody else can lag behind by a few seconds to a few minutes. And that creates a very interesting scale challenges, right? If you need fresh data all the time, that will be the hardest problem to solve. But that's a very important decision to make. And also what kind of search patterns do we want to provide, right? Is it a well-canned search criteria, or do you want to open it up for free form of text? And that also dictates what kind of strategies that you use down at the data layer. And when it comes to data consistency, one of the biggest decisions that needs to be made at the early stage of the development lifecycle is it something that is handled at the application layer, or is it delegated to the database? There are pros and cons to the both approaches, but it needs to be a well thought out exercise rather than something that is that is done as part of the later stage of the life cycle. And again, here, if the data consistency is delegated to the database, now we are complicating the database scale. But on the other hand, if application is handling the data consistency, we're complicating the application. So there is no silver bullet here. It's a trade-off, and that trade-off needs to be a well thought out decision. And when it comes to quality of service, again, this here defines how failures can cascade from a failure in this one service to a system-wide failure unless and until we define that quality of service. In the presence of failure, do you want to fail fast? Do you want to limit the failure to the given service? Are you okay with providing degraded experience to customers? So it means some part of the web page may not work, but other part of the functionality will continue to work. And again, that needs to be well thought out exercise upfront, rather than it being a response to a scale problem observed at the data layer or the infrastructure layer. And when it comes to the system scale strategies, at a very high level, you need to look at it holistically, all the way from database, the infrastructure underneath it, the application, and how your customers are interacting with it, right? How those requirements are evolving, and keeping that eye in mind. So the first thing is you need to demonstrate that how do you scale up deterministically to a point where you understand what kind of concurrency problems show up, how horizontal scale friendly the architecture is. Once you validate that, then scale out obviously makes sense. And as you're designing for it, controlled failures is one of the important things. For example, we talked about fail fast, and the most the complex thing that you can do is not defining what that controlled failure is. That means one service not responding can cascade out to be a connection problem for some other service because you're holding on all the connections. And recovery from, even though this particular failed service recovers a few seconds later, the rest of the system recovery may take minutes. And that is the reason why controlled failures is extremely important when it comes to the strategy. And the stress testing. And if there is one thing that you can take away from this presentation, is the stress testing. Regardless of size of your company, your environment, there is always a scale problem somewhere in the stack. And the art and science of scale strategy is to really identifying what those scale problems are, how they are manifesting in the very early stage, and how you can stress test to 10x levels of volume that you see. And also, how do you monitor for those kind of the scale issues, which is like P95 monitoring indicate that everything probably working fine, but P99 will always show outliers. And it's important to have a lifestyle of having an RCA for those kind of outliers. Is it because somewhere in the system, one component is not scaling well? And along with that, how do you define your testing strategy in such a way that your workloads are tested to 10x volume? And the 10x may seem like a counterintuitive, like that maybe you may have a lot of time ahead to deal with 10x traffic, but that is short-sighted when you consider that when you recover after any kind of a major failure, the catch-up, the increased activity from the customers will show up can show up as a 10x more workload on the database level. It can show up as 10x more workload at the storage level. As simple failure as a network maintenance. And after that, the replication will have to catch up. And it may do 10x more work for a few seconds to a few minutes until it catch up. And that is like a 10x workload happening in reality right there. But there are lots of other areas where you do have 10x traffic happening under our own eyes, but only if we know how to monitor for it, catch those, continue to test for those scenarios, and make sure that that scale strategy is tied to the system scale strategies that we talked about. With that, I will hand it over to Atreya to talk about how we are using Aerospike at PayPal.
Hey, thanks, Sai. Hello, everyone, and hope you're all doing well. So we'll get started now with the PayPal's ecosystem and how we're including Aerospike in the equation. Before we get there, just wanted to provide a brief introduction about PayPal, what we stand for as a leader in digital payments. We also are one of the few payments company with We have 325 million customers and merchants and more than 200 markets. And we also have 700 plus billion payments volume with a year-over-year growth of 23%. Next slide, please. For today's webinar, we're going to use our real-time decisioning architecture as one of the examples for fraud detection and protection applications, and how we designed our database layer underneath that could horizontally scale, that could provide the best experience that our customers or the systems expects as one of the showcasing point, and also drill down into the details of all those designs and considerations. Before we do that, we also will go through the overall database infrastructure at PayPal. Next slide, please. What you're seeing here is overall PayPal's ecosystem of databases, and we serve 8 million executions per second, and more than that, if you see the plus here, and 4,000 database instances. We also have storage that grows year over year 30+%. Storage is 100 plus petabytes as we speak. And amongst all of that, Aerospike is one of the larger fleets of the database at PayPal by host count. And if we go by storage footprint, among the distributed databases, Aerospike also happens to be at the higher end of the storage capacity. Next slide, please. Before we get into the scale and designs, we just wanted to also highlight what's the closest inspiration that we can use as an analogy here to showcase how, and when we plan to design for scale, how does that have to be thought through. In this example here, where on the right side, if you see all the different models of Tesla, and we're using Tesla as an example, different models are designed for different purpose, and also they come with different price points. Model X is the higher end of the price point versus Model 3 is at the lower end of the price point, and a machine like Model S is a luxury sedan. And each of these have different goals. For example, Model 3 is supposed to be designed for mass production. That means at a high scale production, which now translates into how do we get there. That means we have to first define the goals. We should be very clear about what we want to achieve, and then if we work backwards, that translates into having factories or big gigafactories or terafactories that might come in the future, which is extremely huge systems or a huge infrastructure that has to be put in place. Alongside, to be enabling that, it cannot be all done by humans, obviously, and hence it's important to design the robots that can do the work. So that means machines producing those machines is what needs to be designed. And if you work further backwards, what is the heart and soul of an electric vehicle is the battery pack. And the better the battery pack is, obviously you can forget about the overall life of the car, because the battery pack will drive most of those performance related considerations. And while designing the battery pack, it's important to understand how the battery pack has to be maintained, managed over temperature increases, how to be making it safe so that it doesn't blast and something goes wrong with the vehicle. So it's extremely important that all the engineering focus stays on the battery pack. Now, to be able to produce an efficient battery pack, it's even more important that we understand the battery very well. That means what is the battery chemistry, how many cycles can the battery can take over its lifetime, which will define the life of the car itself, and what are the battery chemistry materials that is used so that it can be sourced constantly without any blockages from the sources. So many such considerations are very important to pay attention, and even more important is the cost, so that over a period of time if the resources becomes few to be able to source it, then the cost should not go up. So basically, you have to continuously innovate in a way that we can keep the cost model as low as possible and be able to scale up accordingly. Now, can we go to the next slide, please? Thanks. Now let's define our dimensions so that we can think about developing the solution or building the solutions at scale. So some of the key considerations here would be a storage, which is predictable in nature. So our definition of that was tens of petabytes and could be hundreds of petabytes as it continues, trillions of keys that we want to store in a key value system. So we designed our systems to accommodate all of this, and also there is a limit that we need to define for each of the systems so that we don't go past that limit. And if we were to scale horizontally, that means we have to go horizontal in terms of providing that limit per unit, and then we continue to increment the units. So in those lines, we set a limit of about 10 billion keys per database cluster, and storage of about 240 terabytes per cluster. Consistency in throughput is an extremely important dimension to be carefully designing. So we designed the system to support tens of millions of transactions per second, and we gave an upper limit of 1 million transactions per second per cluster. That means we need tens or hundreds of clusters to achieve the final goal of tens of millions of transactions per second. Latency, we always are very hungry for latency, and we always wanted to optimize our systems to keep it at the lowest possible performance and latency profile. And 1 millisecond for 1 kilobyte object at 99th percentile was our kind of baseline, and today we achieve even better than that. So we knew it is achievable, and with the technologies that we have in hand. We also have to understand at what growth rate are we going to support our systems. Is it going to be 30%, 50%, 100%? And we have to be understanding also that a business growth is not tied to the infrastructure growth. That means a business growing at 30%, 20% a year could translate into even 50%, 100% infrastructure growth, because they are not linear, but it has a multiplication factor which is not easily definable. But if we can, there is a capability that we need to build in place so that even if it is 5x growth in storage, we should be able to continue to absorb it. While we only grow at 2x at the business level. Either one, it is something that we need to be considerate about and also allow the such growths. From the sourcing point of view, we always wanted to have multi-vendor strategy and also have low-cost hardware. And also the components that we use in the designs of the hardware is a commodity components. That means we should be able to source RAM, PMEM, or NVMEs that we use from any of the vendors that we work with. Failure domain, we wanted to optimize around failure domain so that we can build the racks and the servers in a way that we can easily onboard them, we can easily instrument them, and get them going into the data centers. It's also important to understand what is our scale of data centers, regions, and zones. If we understand that, all our automations and everything that requires to understand the deployment strategies can be designed accordingly. So that was one of the key considerations we had in mind. So we set an upper limit of about 4 clusters that could be deployed in a distributed fashion within a given database cluster group. Deployment scale is also important so that we understand how fast do we onboard systems, how many systems do we need to build at any given point, at what rate we want to build it. Then considering developer experience, what should our developers or the application users to should be looking at these systems, and how smooth the experience should be. So those type of definitions we had to put in place, which led us to building automated reporting, automated monitoring and alerting systems on top of what we were putting together as a database infrastructure. Operations at scale was a very critical consideration as well, so that we can keep human footprint as low as possible. That means we don't grow with the human footprint as we grow with at the rate at which we grow the systems. Hence, it was upfront considered as one of the key entry point definition of how do we get there. And all of this was done at the beginning of the onboarding time of Aerospike into PayPal. So we were very clear with the strategy. Hence, it was more of an execution thereafter. Next slide, please. Okay. One of the key, another important point was also the evolution of the data storage and the technology, how each of the different databases, I mentioned about the polyglot system that we have earlier. We have multiple different databases that we support within PayPal, and each technology has its own optimizations around storage technology. And as we saw the evolution of different databases, Aerospike was one of the special ones with hybrid memory architecture, versus we have many systems that is designed around cache. That means data is stored in memory and it is served out of memory. So it turns out to be the fastest among all of them. But that also means it's limited by the amount of memory that a system can support. That also means that it's very expensive solution. On the other hand, in-memory databases are the ones that has data in memory and it is served out of memory, so performance is supposed to be the fastest. And also for resiliency, there is persistence included, but that also means there is quite a bit of cost because there is persistence, and also the data that can be stored is maxed out based on the memory footprint on the machine, which also means the cost. The third pattern is the memory first architecture, where the data is partially stored in memory if it is hot, and as much as it can be kept based on the memory footprint, and the rest is ejected into the disk because once it becomes cold or when the memory thresholds are reached. With these architecture, with memory first architecture, the cost is high, resiliency is also good, but consistency of performance suffers, because if the data is in memory, served out of memory, then performance is great. But then when it is ejected into the disk, and if the data has to be retrieved from the disk, then you fall back on the disk's performance. So that means we cannot define the performance of the system consistently, and hence the applications will suffer depending on the assumptions they make. If the application assumes that the data I just wrote is what I'm going to read, then this particular architecture, memory first architecture, will be fine. But if the application writes the data and reads way later, the performance expectations cannot be defined because it will be dependent on where in the stack the data is residing at that point. On the other hand, hybrid memory architecture provides consistency in performance because data is not stored on the in memory layer, it is stored in the disk layer. And only the indexes are kept in memory. That means we are efficient in storing the indexes. That means our memory footprint should be relatively small. But since data is always in disk, the performance of the database is defined by the performance of the disk. So everything is pivotal. The disk becomes a pivotal decision on, are we going to use hard disks here, or are we going to use SSDs of SATA or SAS SSDs, or are we going to use NVMe? So all of these decisions will actually translate into performance of the database. In our case, we have constantly evolved when NVMe became available publicly and also started becoming better as from the cost and the technology point of view. We continue to innovate and use those latest greatest NVMEs in these databases. Hence, we were able to extract high performance out of it. And most recently, when persistent memory was released, we were able to quickly make those decisions and also be able to absorb that into our designs. And as the fifth option here is all flash, which means data, everything is stored on the disk. That means there is some performance penalty because of disk interactions. It's not as fast as memory. Hence, there will be some degradation in performance. So our sweet spot for the fraud systems that we were designing was hybrid memory architecture. So we zeroed in on it 5 years ago, and we continue to keep that as our primary profile in designing Aerospike databases. Next slide, please. And as we talk through our definition of all these dimensions and how did we implement them, translates into how the outcomes accordingly are seen. For example, in the leftmost picture here, which is a rack design, we simplified our designs of a rack and defined our failure domains to be at the rack level. That means a given cluster resides only in one rack. That means all servers are put in one rack. Now, this is kind of an anti-pattern if you look at from the industry design point of view, which means where the systems are deployed in many racks, which is like rack-aware systems. We took a different choice here for taking the benefit of performance and reducing the complexity of deployment and ensuring that every sub-millisecond that we can achieve by putting everything in one place is what we wanted to extract out of the system. So the designs were performance centric, and hence they were considered to be put into one single rack. And also that gives us low latency and it's predictable latency, and standardized server and standardization also in terms of deployments. And also we kind of have a clear understanding of how many clusters do we want to build on every rack. And even more importantly, we don't deploy racks which are empty, or we don't have to upfront invest into several racks if we were to go by the design of distributed rack designs, and where the database has to be rack aware. We have to invest upfront to deploy several racks at the same time, and that's very hard to sustain and maintain. And we're also not a cloud company where we invest on infrastructure ahead of time. So we, as and when business requirements are there, we invest into the infrastructure as and when it comes. Then if you look towards the right bottom, we had two different SKUs. One was defined in 2015 when NVMEs became available in the market, and also where it was at a price point where we can afford. And we designed for a 6 terabytes NVMe per node with 256 GB of RAM per server. With that, we were able to get about 3 billion keys that we could store, about 120 terabytes of data per cluster with the 20 node cluster design, which means within a given rack, we would store 2 clusters or to build 2 clusters. And in 2020, when we transitioned over to the new SKU, we used persistent memory for the reason that with persistent memory, the indexes in the hybrid model can be persisted on PMEMs, and a reboot does not mean we have to do a re-indexing of all the keys, which was a great relief, because if in the previous queue, if a node goes down, all the indexes have to be rebuilt, which is another 40 minutes to 1 hour, which is kind of defined by the number of keys per node in that design. But in this case, when we translate it into persistent memory using for indexes, the time taken for rebuild of the indexes moves from being in hours to minutes. And in our specific design, we have about 24 terabytes of storage that we chose in our design, and about a terabyte of PMEM, and a max storage of about 10 billion keys that we defined. Per node, we would store about 12 terabytes of raw data, giving some space for compaction and whatnot. With that design, our reindexing time or a reboot time shrunk from hours to 4 minutes. And that's a huge win, because we do patching, which requires OS patching, which requires reboots all the time. And it's a continuous process. That means we'll be rebooting machines every machine could go through reboots every month or even more frequently, which is why we needed this type of technology to be available as soon as possible. So it happened, and we're very happy that we were able to get there. And with the higher indexing capabilities, we were also able to explore higher density of storage, which comes with its own pros and cons. So we stopped at 24 terabytes per node. And also, if you pay attention on the SSDs that we are using, it's a 6.4 terabyte SSDs, and this is widely available with multiple vendors. So that if we cannot get it from one vendor, we should be able to switch to another vendor. Going to the next slide. Can we switch slides, please? Okay, so implementing all of that translated into our systems being capable of achieving, in this case, 6.5 million transactions per second. We have many different workloads that runs on the databases. It could mean we're loading data from an offline system. We're taking live traffic all the time. We're also running database scans for security purpose. There are many different things that happens in the background, and none of those special activities should translate into a real-time experience problem. That means a user who is transacting on PayPal should not see any of this, no matter what type of load we are applying on the database. So the whole consideration of all of these designs were to get the best experience possible while we can hit the database with as much heavy workload as we want and still be unnoticed. And that gives a great customer experience towards the end from the business point of view. Next slide, please. Okay. Now we're showing the operations at scale. So with all those things implemented that we talked about, the dimensions of scale, here is our operations, how it looks like. Today we have 2,400 servers just for Aerospike. We're serving our traffic out of 130 clusters. They're distributed clusters in different availability zones and different groups of databases. We have about 40 different groups of databases within which there are multiple clusters that are deployed in multiple availability zones. And they also do, they also synchronize between themselves by replication, which is Aerospike's native XDR replication. And we are serving about 6.5 million transactions per second and at different peaks. We also do 6+ upgrades per year, which involves OS patching that we could be doing in the background. We could be doing software upgrades. We might be building clusters in the background. So there will be several different types of activities that goes on in the background. And all of that is powered by Ansible automations that we have in-house developed to manage the entire life cycle. No single commands are executed on the database for administrative purpose. Everything goes through Ansible, and all of those designs in the Ansible layer or the automation layer has helped us scale tremendously, whether we provision in the database, whether we maintain the database, whether we are rotating certificates due to expiry of the certificates, or whether we're doing software or OS patching upgrades. All of that is being handled by a very small team. In this case, there are 2 dedicated database engineers who work on Aerospike, and they're supported by 2 other members on and off, depending on if there are production issues or support that is required. But they're mostly a horizontal operations team who works on and off on the systems. We also support internally about 5 different environments, and these systems are deployed on 65 different racks. So looking at all of this scale, the human footprint we have achieved is the smallest of among many different systems that we have designed, and all of that is because we, from the get-go, we designed for bringing the solution with scale in mind, and that has been the main reason why we're able to be where we are today. Next slide, please. All right, so wrapping up on how do we achieve scale and how this all translated into and how we overlap with this analogy is the battery technology that we were discussing earlier in the PayPal's context is kind of Aerospike as an analogy here, which is what powering our database systems. And underneath the Aerospike database technology is the NVMe SSDs that Aerospike specializes in to achieve high performance. And as an icing on cake, persistent memory became a huge win for us when we added that into the equation of our SKUs. So that gives us a powerful battery, and now using that battery, we're able to design our battery packs, which is rack/clusters per rack. To achieve scale and low human footprint, we translated that into an Ansible automation, lifecycle automation APIs, which is able to deliver us with all different kinds of user experiences. And today we are keeping everything simple, and hence we use Aerospike as a key value system. And it takes the huge workloads to be able, and horizontally serves several use cases, and majority of the use cases are key value, that is 98%. Out of that 98%, 8% specializes in supporting online graph use cases. What this means is we can develop our own graph solution on top of key value system, and all of that is managed by the application, while the database performs at millisecond experiences. And with that, we're able to serve online graph queries with 2 hops as an upper limit within few milliseconds, which otherwise would be not possible for us to horizontally scale for a graph system and also be able to serve at low latencies, and because of limitations on the graph designs or the graph database designs. UDF is a small use case that we explored. We also continue to support that, but it comes with its own complexities of because we manually inject user-defined functions, so we have to be extremely careful. But it's also one of the ways to compute in place within the database anything that we can distribute across applications. So we have some unique use cases, but it has served us all the given us all the options to explore Aerospike to the best possible way. That comes to the end of my talk, and I'll hand it over to Srini to take over the next ones. Thanks.
Thank you, Atreya. So let me just spend a few minutes on the underlying technology of which implements hybrid memory architecture. One of the important developments that has happened over the last couple of years is the availability of Intel's Optane persistent memory. It has added another, I would say, storage layer, which has some very interesting characteristics, as you saw when Atreya described his system and how it got affected by it. So what Optane provides is something which is almost as fast as DRAM, but with the ability to have much larger capacity. Now, Aerospike's hybrid memory architecture essentially depends, it was invented about 10 years ago or more, where we combined an index in DRAM with data stored in SSD. And Optane has provided the ability for us to store indexes in Optane and then continuing to store the data in SSD, thus increasing scale. Let's go to the next slide, please. So if you look at the original hybrid memory with DRAM and flash, what Aerospike was able to do for many deployments, including the kinds of deployments you've seen today presented by Sai and Atreya, is the ability to reduce cluster sizes from maybe hundreds of nodes down to a few dozen. And that is because given the hybrid memory architecture with the index in DRAM and the data in flash being random access for accessing data reads and writes directly from flash, and we also obviously had to deal with wear leveling for writes to make sure that writes are done with large blocks and reads are done randomly. And the end result was you could store dozens of terabytes in a flash based instance, the scale up that Sai talked about, therefore reducing cluster sizes by an order of magnitude. Now, moving on to the second aspect of it, which is an additional kind of scaling level based on storing the index and PMEM, what we could do is we could reduce or increase the scale up by another 2 to 3x. And that's essentially effectively what happened, while having minimal impact on performance. And that is really critical, because we talked about the requirement in the introduction about having sub-millisecond reads and writes for databases. What we have been able to do is over the years is to provide it for even more and more data on a per node basis. Combined with the scale out of the database, you now have small cluster sizes which can handle 100 terabytes or more of data. Typically into 10 to 20 node cluster sizes can handle really, really large amounts of data in real time. The next, please. The other thing that Atreya also mentioned is when Aerospike implemented support for index storage in Intel's Optane PMEM, we made sure we used the native APIs for App Direct, as they call it, and ensured that the index can be stored persistently, and we could restart the system with the index on the persistent memory. And that's what you see here. You see here a huge reduction in terms of the time it takes to build the index from scratch from the data if the index wasn't stored properly, versus restarting the system. As Atreya said, instead of hours, it goes to minutes. And in this particular case, it goes from about 80 minutes to under a minute, as shown by Intel. So this is a very important lesson, is when leveraging new storage technology, it's important to use all of the features available in the new storage. Just using the PMEM as additional RAM only gets you so far, whereas we have enhanced, or we have leveraged and utilized the features which are native to PMEM and unique to it to enable this kind of performance for restarting a node. Next, please. Okay, so the problems that we talked about today were related to the work that PayPal has done, but I can assure you, based on deployments of Aerospike customers that is shown here, that these problems are across industries. The march of better user experience based on analyzing and leveraging recent user behavior is just continuing into more and more industries like financial, fintech, telcos, gaming, e-commerce, etc. Next, please. So to summarize, the key takeaways from this seminar, from this webinar, is that the data is really critical for providing a better user experience. But we need to use data which is both recent and accurate. And this leads to much better decision making on behalf of customers and consumers who are accessing various services. It is just not enough to have data itself, but the real-time insight that you can provide by the processing that happens across this data is also really important to provide really good fraud scores and so on, to minimize false positives, for example, which could really be a big problem for user experience if we don't minimize it. It's also important to have a certain SLA to all of these real-time apps so that the user experience stays extremely high value. Intelligent internet apps fundamentally need a database that is optimized for new storage technologies. And the goal here is that you can now ride the Moore's law cost curve of these storage technologies so that you can provide better economies at scale. And that's really critical to be able to make sure that your business can grow unimpeded to the 10x and 100x that Sai talked about without having to have any technical deficit. Thank you.
Okay, great. This is Cheryl again. Thank you, gentlemen, for a really, really informative webinar. There's a bunch of questions that we do have. I'm not sure that we're going to have enough time to get through all of them, but we will follow up after the webinar. One question that I think will be a quick one is to Threya regarding latency. Threya, you mentioned 1 millisecond with latency. From a networking perspective, does that include network time?
Yes, it's an experience as seen from the application side. It includes network and the database performance as well.
Okay, great. And then one last question, Srini. So, when you're optimizing for new storage technologies, how do you make sure that Aerospike is able to keep up with that as new technologies are released?
Well, it is something that we have some experience with. When we started the company 10 years ago, we focused on SSDs, which were just becoming popular. Even at that point in time, we ended up delivering what we call as an Aerospike certification tool for SSDs and created partnerships with a lot of storage vendors like Intel, Micron, etc. And we have continued those partnerships over the years. And as new technologies like Intel's Optane persistent memory showed up, we were well positioned to collaborate with storage vendors. So to some extent, a lot of it is just paying attention to what's going on in in other related areas and working with other vendors in terms of partnerships. So the way I think about it is the Aerospike provides the software, but really it is standing on the shoulders of all the investment that is done by various storage vendors and also processor vendors and so on. So we're simply leveraging these technologies and staying on top of it by working with them.
Okay, great. And we are at the top of the hour, so I want to thank everyone for a great presentation and pass it back to Drew to wrap us up.
Thanks, Cheryl. Thank you to you and Srini and Sai and Athreya for a great presentation. I would also like to thank Aerospike and Intel for providing the audience with a great webinar. Lastly, thank you to everyone who attended today. We hope you learned something new that will help you in your developer career. Have a great day.